Alright folks, welcome to the lesson on parallel lines and proportional parts. What we're doing in this lesson is drawing parallel lines inside a single triangle and showing you the theorems that result, specifically theorems that relate to how the parallel line within a triangle cuts the sides of the triangle into proportional parts. And so let's jump straight in to theorem 7.5, the triangle proportionality theorem. We already know that if you have parallel lines inside a triangle, it's going to allow us to have triangle ABE proved to be similar to triangle ACD, and we can do that very easily using corresponding angles once we've got the parallel sides. And so we could prove a similarity between the large and the small triangle using AA. This theorem is not focused on that. What this theorem is focused on really is to explain that in addition to all of the corresponding parts of the two triangles I just highlighted, that segment ED and segment BC are also cut proportionally by the parallel lines. And so what that basically means is we can treat them as additional corresponding parts of the triangles, even though they only fall into one of the triangles and they're only part of the side of one of the triangles. But we treat them as if they are corresponding parts of the similar triangles. Okay. The reason why this is true, if you cannot sleep at night without understanding why this is true, so what you'll find at the end here, there are a couple of theorems which you can go through the proof of the theorem, which will explain why those hold true. The triangle proportionality theorem proof is here. Also, you may recall from the previous lesson we had an angle bisector, triangle angle bisector theorem, which also told you that if you bisect the angles of a triangle, it cuts the opposite side into the same proportion as the other two sides. And so this is a proof, or at least the beginning part of a proof, and so that will help you to understand why those theorems hold true. Okay, so let's go back to actually using the theorem. So we're not going to spend any time in this video going through the proof of them. And so in this first example, really what we're being asked to do is to determine which of these statements are true and which of them are false. And so to help you with that very quickly, what I'm going to do is I'm going to mark the sides of the triangle that are corresponding. And so side FH is going to correspond to side FA. So this is based on the fact that triangle FHT is similar to triangle FAB. Okay, and so let me write that up quickly. So triangle FAT would be similar to triangle FAB, and that would be because of AA. With our parallel lines and our corresponding angles. Okay, and so let me come back over here. Similarly, we would have side FT would correspond to side FB, and finally, in the case of the triangles, side HT would correspond to side AB. And effectively, what the theorem is telling us is that in addition to the corresponding sides of the triangles, the segment HA is going to be a corresponding side and will be cut proportionally. And similarly, segment TB, we're effectively going to be able to treat them as well as if they are sides of the corresponding triangles. Okay, so let's just go through. Here in the first one, we have FA over HA. So the whole side of the large triangle over the portion, and then we have got FB over TB, and you can see hopefully from the colored markings that that is a perfectly acceptable proportion, and so that one is in fact true. And so what I'm going to do in the interest of time is just complete the true-false statements, and then I'll give you a very quick explanation of why certain of them are false. So go ahead and try them yourself. Okay, and so hopefully those correspond to what you determined. Both D and E are in fact false, and so I'll show you very quickly why. In D, we have got FA, which is that side, over FH, those are corresponding sides. And so what we should be able to do is establish a ratio using two of the yellow sides in this particular case, or the two orange sides. And so what we've got instead is ft, which is a good start, but the problem then is when we have tb, what you can see is that is not a corresponding side. That does not correspond to FA. It should have been FB, and so that one is in fact not true. That is false. And then the next one that creates a problem for us is FH over AB, and so I'll change colors. The diagram's getting a little messy, but we have FH again, so I'll mark that over in red, and that is on top of AB. And immediately, hopefully, you can spot what the problem is. We've got green over orange, and you can see the three green parts that correspond are FH, HA, and FA. And as soon as we've used one of the orange parts, that's a non-corresponding side. And so straight away, that's going to make that a false statement. The others are true. Hopefully, you'll be able to see that the reason they're true is that the corresponding colors, if you will, are matching. That's a really helpful way to be able to look at these. Okay, all right, and let's move on to our next example. Okay, so basically the idea in this example is to use the same theorem, but this time to use it to solve. And so once again, what we're interested in doing is determining which sides correspond. Since we've got our parallels, we've got similar triangles, but we also have this segment is going to be in the same this segment over 12 is going to be in the same ratio as any corresponding sides from our similar triangles. Okay, and so once again, these are our corresponding parts. This corresponds to the whole of this, which also corresponds to this piece, and then x corresponds to 24. And so hopefully that will very easily help us to set up the correct ratio. And what we're going to do in this particular case is we're going to use x with 24 because they're corresponding. And what I can do is use 8 in combination with the x, and then I can use the full length over here in combination with the 24. And so we could say x is to 8 as 24 is to the full length of this side, which of course can be very easily obtained by just adding 8 plus 12. So that's where we get the 20 from. And then x is going to be 8 multiplied by 24 over 20. So we're cross multiplying or multiplying both sides by 8. And so we'll just clean that up a little. So what's that? 192 over 20, which you can leave like that if you want. You're not required to simplify, but if you did want to simplify, what would that give us? That would give us 9.6, I believe. Yep, I think that's 9.6. Okay, and then we're going to go ahead and solve for y, and then in the case of y, once again, what we want to make sure is that we're using corresponding sides, and so we've got 10 and y, and we've got 8 and 12. We know all of those lengths, and so we can set the proportion up using those. I'm going to say y is to 10 as 12 is to 8, and I'm just going to try to make sure that I put y on top. It's a little bit easier to solve, a little bit less work. So I'm going to cross multiply again. Y is equal to 10 by 12 is 120 over 8, which is going to be 15. Okay. And so this theorem, the triangle proportionality theorem, is in fact biconditional. And so what that means is its converse is also true. And what that means is if we can show that the ratio of AE to CD is the same as the ratio of EB to DB, then we can prove that the segment ED is in fact parallel to AC. So that's just the triangle proportionality theorem in reverse. Okay, and so now we're going to use it to determine if that's true or not. And so if the ratio of 6 to 8 is the same as the ratio of 9 to 10, then that would prove that AC was parallel to ED. And then the flip side is, of course, if those are not the same, then it proves that the sides are not parallel, and in turn, of course, that the triangles are not similar. And so don't assume that triangle ABC is going to be similar to EBD, because we don't know if AC and ED are parallel. And so we have to make sure that that is true first. In this particular case, 6/8 simplifies to 3/4, and of course 3/4 and 9/10, that's 0.75. And this is 0.9, and those are obviously not equal, and so that means side AC is not going to be parallel to side ED. Okay, moving on, we have another small extension of essentially the triangle proportionality theorem, and that is when the parallel lines, instead of just cutting the sides of the triangle proportionally, in fact cut them into a proportion or ratio of 1 to 1. And so in other words, what it means is this time JK joins the midpoints of two sides of a triangle. It's the exact same idea as the trapezoid midsegment, and so you may recall we did the trapezoid midsegment theorem that said the line segment joining the midpoints of two sides of a trapezoid is parallel to the third side, and its length is the average of the trapezoid's bases. This is a very similar theorem. The line segment joining the midpoints of two sides of a triangle is parallel to the third side and equal to half of it. And so in this particular case, of course, there isn't another side that you could average out the length of, and so JK is just half of FG. Okay, so we're going to go ahead and apply that to example number 4. Okay, and so I'm going to point out a few important things here. So first off, since E is the midpoint of BC and F is the midpoint of AC, then segment EF is going to be a midsegment, and what that means is it is parallel to the third side in the triangle. In other words, EF and AB are going to be parallel and equal in length to half of the length of side AB. So as you can see here, side AB is equal to 15, and so segment or side EF is going to equal half of that, and that's where we get 7.5 from. So the length of EF is going to be 7.5. If we then move around, what you'll see is that D is a midpoint of side AB. We can see, once again, obviously, we're going to reuse point F as the midpoint of side AC, and that means that segment DF is also a midsegment of the triangle. So segment DF is going to be parallel this time to side BC, and the length of DF is going to be half of the length of BC. Since we know the length of DF is 9.2, we now know that the length of BC is 18.4, and of course, since BC is cut in half, each of these pieces will be 9.2. Okay, and so in answer to the question, what is the length of EC? We have a length of 9.2. Okay, and then last thing just to pay careful attention to, hopefully you've already picked this up, but if you look very carefully at the quadrilateral over here, we have established through the triangle midsegment theorem that those sides are parallel. We've also established that these are parallel, and so hopefully what you were able to recognize is that DBEF is in fact a parallelogram. And so we've been asked to find the measure of angle DBE, which is the measure over here, and hopefully what you're able to see relatively easily is that since we've got parallel sides, we've got our F over here, corresponding angles are going to be congruent, and angle DBE is 86 degrees. Okay, really pretty soon we're going to be running out of time, and so what I'm going to need to do is continue and complete this video in part 2.